Hello friends, today we're going to be looking at topic 2.6 in Brian Passwater's material. And so here we're looking at competing function model variation. In other words, we're looking for the best fit. We're going to have some data, we graph the data, we plot the data, we put the points on the graph, and then we see which is going to be the best one. There are three types of functions that show up again and again in math, and I would say in physics as well. And those are linear, quadratic, and exponential, right? On the AP exam, you'll be given some data, and you've got to be able to work with that data and use a graph or use just the table and figure out what kind of function it is, whether it's linear, quadratic, exponential. So, linear graphs are simple. It looks like a line. There's a line there. The points form roughly a line. Notice the points are not all perfectly lined up with the line. Right, it's kind of going through the middle. Again, what I usually call in my physics classes a best fit line. Same is true for quadratic. You can see this curve, the quadratic curve, going kind of through the middle of all the points, but maintaining the shape of a quadratic. And then exponential as well. The whole idea is that we have some measured values, and the way the measurements are taken may not be exactly perfect. And so this assumption that we make, but it works out on further investigation. But the assumption that we make is that the way that the measurements should have happened should have been according to one of these types of functions, which is an interesting thing, right? Just the fact that we can model processes in the world, in finance, whatever it is, and that there's enough regularity with it that the measurements, the quantities, can give us these kinds of relationships. Okay, so let's take a look. Example 1, I've already put some dots on there, 1A, and when we look at it, this looks like it's going to be linear. And I've got a handy little tool on the iPad here. I can make a straight line. If I wait a second, it like snaps to make a straight line. And you can see this is going to be a linear function, right? B, it goes up and then comes down. That's not linear. It's not exponential, right? Exponential just goes up or just goes down. And so this is going to be quadratic. Right? I don't have an automatic quadratic drawing tool, but it'll be something like this, kind of going through the middle of all those points. I can try that again. That's messy. Anyway, you get the idea. And it doesn't have to be perfect, just have to be able to identify it as quadratic. 1C, this one is going down, but it doesn't look like it's going in a line. It looks like it's going in an exponential style down. Right, so this one is exponential. This would be decay if it asks for it. And then D, going up, so this is exponential growth. All right. Now, going back to graphing these things using our graphs, and then there's a topic that came up before, but now we're going to look at it with a little bit more detail and look at what it is that we can learn from the residuals. So the residuals, what we do is we can create the model, and then based on the model, we predict what a value is going to be, or we say what should a value be based on the model, and we compare that with what the actual measurement is. The difference between the predicted output and the actual measured value is the residual. Okay, so the actual output value minus the predicted output value, that's how you calculate the residual. If we take a look back at the weight of newborn babies, I don't know, this might be the same data that we looked at before, but same kind of example. And so I'm going to take this table, I'm going to put it into Desmos, and we'll take a look at it there. Okay, so I put the points in, and it asks me to create a linear function out of it. So the linear regression, again, what I do is I'd hit the plus sign in the top left, I added a table, I put the values in, and then I hit the button that looked like a line going through 4 dots that showed up next to the one just under the plus sign in order to get the regression model. And I pick linear regression. And so the function I get is y equals 0.8x plus 3.34. Question C is saying that another baby was measured at 2.5 months and was 5.5 kilograms. They want to know what is the residual for this weight. Okay, so what we can do is we can use this function, we can use this model to predict what we think that should be. Okay, and so the way that I can do this in Desmos is next to the function, there's a little thing that looks like it kind of looks like a lined piece of paper with an arrow going into it. So what I'm going to do is I'm going to click that, and then it produces the function for me again in a new line. And then from this, I can hit the gear button, and next to the function, there's a table button. So I click the table button, and now I have a table. And so I can put in there 2.5 as the value, and the output is 5.34. So the actual weight is 5.5, so the residual is 5.5 minus 5.34. That is 0.16. Okay, so the model is underestimating the weight of that particular baby. And we can use the residuals to check how appropriate a model is. So, for example, let's go back to Desmos for a second. You'll notice that down towards the bottom right, it says residuals E1 plot. So I can plot this. And so it actually gives me in the table the residuals. It tells me what gives me those values. And it looks like there's a little bit of a pattern, but there's not a huge pattern. Watch what happens if I try a different type of regression. So when I try an exponential regression, notice that the pattern of the residuals is really pronounced, right? More so than the linear regression. So when there's a definite pattern to the regression plot, then I know that I probably have the wrong function, right? If it's pretty big, if there's quite a variation there and follows a particular pattern. And so, interesting, it kind of looks like the quadratic model is the best one for this, even though they're telling us to use linear. So in example 3, we're told that a exponential regression was used to model a data set. This is the residual plot. And so what's the best conclusion, looking at this residual plot, what's the best conclusion about the exponential model that we used? Well, the answer is that the exponential model is appropriate because the residuals don't show a pattern, right? There's kind of that, looks like it's kind of random. Here are some other examples that might help. So a group of pre-AP Calc students used a set of data to create linear, quadratic, and exponential regression models. After creating the models, they created a residual plot. Okay, and so the residual plots are what you see there. Which is the model that is the best fit for the data? And the answer would be the exponential, because there's not really a pattern to the residuals. The linear regression, there's a definite pattern there. The quadratic regression, there's definitely a pattern there. And so the exponential model is the best one. Okay. Here's another example of a couple of different situations, and we're trying to decide what do we think is going to be the best kind of model for the quantities that we're looking at here. Mr. Passwater is going to be doing a lot of painting, and he's going to be painting circles on the sides of buildings. And so he wants to create a model for how much paint is needed in quarts for a circle of radius r. Well, a circle of paint, right, that's area. You're covering the area with the paint. And the area of a circle is pi r squared. And since we're looking for a relationship with the radius, paint to radius, then we're going to want a quadratic model for that. So after he creates this model, he's going to use that to predict how much paint he should buy. Should he overestimate or should he underestimate? You know, thinking about kind of the way that residual works. And the answer is that he should overestimate because he doesn't want to have to run out of paint. Right? So he should overestimate the actual amount of paint needed. So that's it for this topic. Thanks for watching. Don't forget to like and subscribe.